Now we're getting into the sort of nitty-gritty that's associated with gas laws. And the primary nitty-gritty that we run into here is that when you look at gases, we're assuming right now that all gases are moving at the same speed. But in reality, they're not. They're moving at kind of an average speed. So if you look at any graph that's associated with this thing, okay, so here's molecular speed or atomic speed if it's an atomic gas. Okay, and so up here is the percentage or the frequency of molecules. Molecules, right? So percentage of molecules over here, molecular speed on this side, all right? What this means is that at a certain temperature, I'm going to get things moving at different amounts, okay? If you think about it, things get cooler, they slow down. And when they slow down, you have sort of like a larger grouping down here. So let's use blue. Hopefully this blue marker works. That's not too bad. So when things are cold, right, I'm going to have a larger group of molecules that are lower on the molecular speed table, right? As I heat things up, right, I'm going to see a gradual broadening of this curve, okay? This means that more molecules are moving on average right around here. So when things get average, my average speed increases a little bit. And this makes sense. As I raise the temperature, things will be moving a little bit more, okay? So this is related to temperature, molecular speed related to temperature. As the temperature goes up, this is why I'm using these colors. Blue for cold, green for hot, or green for warm, orange for the next color, okay? So as these things warm up, I'm going to get a greater distribution of speeds at that point, okay? And finally, when I get down to reds, I'm going to see more of a flattening here because of the high speed that's associated with all of the gases, right? And what this just means is that at these temperatures, I don't really have all the molecules at once moving at the same speed. Instead, what I have is a speed which is, let's see, a speed which is sort of average based on all of the molecules' speed. Like if you look at the red one, my peak is right here, right? And I've got a lot of molecules spread out. So I look at this, I'm kind of looking at the average speed that's associated with these things. Now, average speed is one thing, but one thing that we'd like to do is use something called the RMS speed. Okay? And RMS, and it's all lowercase, so RMS, what this stands for is root, this is mean, and this is square. Okay? And the root mean speed of any given material is the square root of 3 MRT. Okay, so here's the square root, so that's the root part of it. Okay, and this is 3 times RT over phi cm. Okay? And this is what we're going to call the U. The U here is the representative of the average kinetic energy that's associated with things. It's a little bit different than the average speed, okay, when you actually calculate average speeds, but the RMS speed, what it does is it sort of smooths everything out. It keeps negatives from throwing your values off when you get into average values. Okay? Because what I'm doing, right, with the 3RT here, I'm square rooting the average speed of the molecules. Okay, so my RMS speed is due to a function of a square root. Okay, so I get this average RMS speed, and what that does is it talks about the kinetic energy that's associated with each one of these molecules. Okay, and that has to do with two effects. It has to do with diffusion and diffusion. Let me erase the board, and I'll put that back up there. So the first thing I'm going to talk about is effusion. Okay, so this is effusion. And effusion has to do with how well gases are escaping from a container. Okay, if you think about a balloon, as you blow it up, it stretches, right? Okay, but it's somehow keeping all of that gas inside, even though the material is stretching. When that material stretches, though, you're creating tiny microscopic little holes in the polymer system of that balloon. So here's my balloon all stretched out. But what is stretched out like that is not as thick, which means that the gas, when it's small and tiny, can penetrate those holes. Now, if you've ever had a helium balloon, it's fun for like the first couple of hours. Yay, my balloon's high in the air, right? And then it gets lower and lower, then it just sort of floats around until it ends up on the floor. And that's a function of effusion, okay? And what effusion has to do with is the rate at which the gas escapes from its container, okay? So this is called Graham's law, right? And Graham's law has to do with this. So it has to do with rates. And both of these rates, R1 and R2, are equal to, okay, square root of 3 RT over the molecular weight of 1, for fancy M of 1, 3 RT over fancy M of 2. Okay? Now, if you remember your math, and I hope you all do, if you remember your math, these things can be combined, okay, to a certain way, right? If I take these two things, I can take the entire square root of the system. Now, notice 3 RT are the same in each part of the system. So one way of looking at that is saying 3 RT, okay, and it's going to be equal to M1 over M2, okay? 3 RT M1, fancy M1, 3 RT M2, okay? Now, if I look at these two things, because of the nature of they're on top of each other as far as fraction goes, the RTs cancel out, okay? But this is a 1 over M, so what happens is the M2 moves to the top up here. So fancy M2 over fancy M1, okay? And that's still square root, okay? Good. I just had to double check, make sure my math was right. Okay, so we have M2, fancy M2 over fancy M1. Okay, so R1 over R2 is going to be equal to the square root of M2, fancy M2 over fancy M1. Notice that the 2 and the 1 switched on the nature that they were both in the bottom when I did my comparative scale at that point. What this tells us, okay, at this point, is how easy it's going to be for different gases to try to move through a certain permeable barrier. So if you think about a helium balloon, compared to oxygen and other things, oxygen's trying to penetrate the balloon, trying to get in. Helium's trying to escape. The rate at which helium escapes, because helium's teeny tiny, it's only got an atomic weight of 4, right? If you think about oxygen or air, oxygen's got O2, which is 32, nitrogen is 28. These things are much larger than the helium, so these molecular weights are much higher, okay? So that means that the rate of 1, okay, this is smaller than the masses of 2, okay? So this number, okay, when you look at it, tells us that R1 is going to be somewhat large, okay? And that makes sense when you're comparing the two. So that means helium is going to escape from our balloon faster than oxygen can penetrate it, which is why your balloon deflates over time. So when we talk about diffusion, diffusion is the ability for a gas to go from one place and spread out, okay? I call this the fart factor. Whenever somebody passes gas, and it takes a certain amount of time for that gas to diffuse to the room, for everybody to smell it, then say, oh, why did you do that? Okay? Diffusion occurs in areas, and as things spread out over a certain amount of area, they will become more diffuse. And diffuse means dilute, right? If you think about it solution-wise. So the gas is going to dilute itself over a certain amount of area. And this is due to diffusion, okay? And diffusion is also associated with effusion, and it has to do with how fast something is going to move through the air. Okay? Things that are smaller are going to diffuse a little bit faster. Things that are heavier are not. If you know anything about nuclear proliferation, there's a big word for you, nuclear proliferation, right? One thing people are worried about is centrifuges, okay? And if you think about a centrifuge just spins something so that something that's heavier goes to one end and something that's lighter goes to the other. So generally, when we're looking at centrifuges, we're trying to take uranium, not O6, it's F6, okay, uranium hexafluoride, okay, which is a gas when we heat it up. So you take uranium hexafluoride, and there's 2 different isotopes of uranium that we're interested in. There's 238, normal uranium, a little bit radioactive, not really anything anybody really sneezes about, We're in a Geiger counter, everybody goes click, click, click. It's not really exciting. When we purify that, when we look at uranium-235, okay, uranium-235, This is the stuff we can make a bomb out of. Okay, so to make this pure, what we do is we heat these gases up, and then we start passing it through a porous membrane. Okay, as we're spinning this stuff. And because 238 has a higher mass than this one, okay, if you remember Graham's law, R1 over R2 is equal to the square root of the concentration of fancy M2 over fancy M1. Okay, fancy M, anything that's lighter is going to push through the system a little bit better. Okay, that's what we proved with the helium in the balloon. So what happens here is that the 235 is going to push through this membrane and collect on one end in greater concentrations than the 238 on the other end. So this is how we can separate these isotopes out using a centrifuge. Okay. Now what they don't tell you, and this includes in the video, if you're looking at uranium rods for fuel, you only need about 6% enrichment. What that means is that you just need to get a little bit more uranium in these things. Get rid of the fluorine, melt it into solid uranium. That solid uranium is going to be enriched, and that means that it's good enough for nuclear fuel, for uranium fuel. If you want to make a bomb, you got to go up to, say, 98%, 96 to 98%, which means that if somebody's got 30 centrifuges, odds are they're making fuel. Somebody's making 30. If somebody has 30,000 centrifuges, odds are they're making a bomb. So listen to those when you listen to the news and they talk about these things. A lot of times they'll talk about them without ever really knowing what they're talking about.